All right, hi everyone. So today this lecture is going to be about Kepler's laws. So just an overview of Kepler's three laws. The first law is called the law of orbits. It's that all planets move in elliptical orbits with the sun at one focus. Law number two is the law of areas. A line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is the rate dA over dt, at which it sweeps out area A is constant. And then last but not least, law number three, the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So it's a lot of information, but let's kind of go through them one by one and talk about what exactly they mean. So number one, the law of orbits. Now here we know that all planets move in elliptical orbits with the sun at one focus. Now an elliptical orbit is shown on the right-hand side here. When we have a elliptical shape like this, we have two what we call foci. So we can see that the sun is at one focus, and then this is our other focus here. Plural is foci, I'm pretty sure. Or one focal point, one of two focal points. Now there's a bunch of different letters here, and so we'll talk about what these things mean as well. So here we assume that the mass of the sun, that big M, is much, much greater than our little m, or the mass of the planet, so that the center of mass of the planet-sun system is approximately at the center of the sun. Now A here, which we can see in the figure, is this distance right here. This is called the semi-major axis. And what this means is it's basically the largest radius, kind of this elliptical shape, okay? So that's called a semi-major axis. E, which is a little e, we call this an eccentricity. And so this is the measure of how much a conic section deviates from being circular. So what this means here is that basically the larger this distance EA is, the larger the eccentricity. So EA, which is this distance right here, so from that focal point to the center of this elliptical shape, that's our distance EA, the distance from the center of the ellipse to either focus F or F prime. So eccentricity is going to be 0 when we don't have an EA distance. And that is when we have like a circle. So for example, our eccentricity in this figure right here, it's very, very small because that EA distance is very, very small. So we're closer to a circle here. All right, now when our shape is closer to a ellipse, then that EA distance is going to be much, much greater. It's closer to 1. All right, and EA, that eccentricity, is between 0 and 1. Okay, so eccentricity is 0 for a circle where two foci merge to a single central point, and eccentricity is between 0 and 1 for an ellipse. A small e, or eccentricity, means a small EA distance. And then for the Earth orbit, the eccentricity is only about 0.0167. So basically what this means is, yes, the Earth's orbit is an ellipse. However, the eccentricity is so small that it's very, very close to a circle. So that's why we can kind of model the orbits of the planets as circles instead of ellipses. Ellipses? Such a weird word. All right, example, or law number 2, we have the law of areas. So this says that a line that connects the planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is the rate dA over dt, or the area as it changes with time, at which it sweeps out the area A is constant. Now, the main takeaway here is that the planet moves the most slowly when it's furthest from the sun and the most rapidly when it's nearest to the sun. And we already did talk about this in class. But here we can see that because this area has to equal this area right here, because they're both sweeping out these areas in 1 month, the time, we have the same time, 1 month for each, but the distance that it covers here when it's farther away is smaller than the distance that it covers here when it's closer to the sun. So therefore, we're moving slower when we're farther away from the sun, we're moving faster when we're closer to the sun. So that's our main takeaway from Kepler's law number 2. And then finally, law number 3, this is called the law of periods. So I'm going to kind of derive the equation for you here, and then we'll talk about what we get from this equation and what it means. So we know Newton's universal law of gravitation is G times m1 times m2 over r squared. We also know that this can be modeled as a centripetal force, even though, of course, they're elliptical orbit shapes. But because those eccentricities are so small, we can model it as a centripetal force, which is mv squared over r. We then take these two equations, set them equal to one another. So what we get here is mv squared over r equals gmm over r squared. In this case, I'm going to call the mass of the planet here mass 1, so that's going to cancel out. R will also cancel out with that squared term right here, so we end up getting v squared is equal to g times big M, which in this case we're talking about the solar system, so this is going to be the mass of the sun divided by r. And then we also know that since we're talking about circular motion, we can use v is equal to 2 pi r over period for our velocity, because we have a circle, right? The distance that that thing is traveling is the circumference of the circle over the time for one complete revolution, which is period. So we get circumference over period, which is 2 pi r over period. And then here we're going to square that because the v squared equals gm over r. So squaring that whole thing, we get 4 pi squared r squared over period squared equals g times the mass of the sun divided by r. Now what we're going to do next is we are going to cross multiply. So cross multiplying, we get 4 pi squared r cubed equals gm times period squared. And then from here, what we're going to do is we're going to divide both sides by big G, our universal gravitation constant, and the mass of the sun. So we get this equation, and this is the first important equation that we want to use when we're talking about the law of periods. And then also, if I divide both sides by r cubed, I get this equation as well. So these last two equations are very, very important when we're talking about the law of periods. So first equation here. This equation gives you that definition that I gave you at the very beginning of this lecture. So remember, I told you the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. Now here we're just, again, we are making this simple, and we're saying that the orbit is elliptical in shape, but we can model it as a circle. So R really is equal to the semi-major axis, which was that A, if you remember from the figure at the very beginning of the lecture. So we can see that the period squared is proportional to r cubed here. And then also when we divided both sides by r cubed, what we got was period squared over r cubed is equal to 4 pi squared over big G, our constant, times m, the mass of the sun. Now, this is the reason that we call this third law the harmonic law. So for any central body, and in this case, we're talking about the sun in the solar system. We can also talk about like Jupiter with its moons orbiting around Jupiter or something like that, or the Earth and all the satellites orbiting around the Earth. So any central body, the sun, Jupiter, the Earth, anything that other things are orbiting, has the same ratio of period squared over r cubed for every single planet that's orbiting it. Now, the reason for this is that this ratio right here, this 4 pi squared over G times M, is going to be the same because G is a constant. 4 and pi obviously are just numbers, so those are constants as well. And then M is going to be the same for every single body that's orbiting because M is the mass of the central object. So the sun or Jupiter or Earth, whatever we're talking about as that central body. Okay, so since this whole number right here, 4 pi squared over gm, is the same for every single thing that's orbiting that central body, then every single thing that's orbiting that central body is going to have the same ratio of t squared over r cubed, and we call this Kepler's constant. Okay, so with Kepler's constant, we can then find like a period for another satellite, or maybe a distance r for another satellite. So say you knew the Kepler's constant for the Earth, or say you knew the period of one of Jupiter's moons and the r distance for one of Jupiter's moons. Well, if you knew the r distance for another of Jupiter's moons, you can then solve for a period of that second Jupiter moon. Okay, because again, this Kepler constant, this period squared over r cubed, is going to be the same for every single satellite that orbits the same central body. Now, one last note on this, Kepler's constant, sometimes you see r cubed over period squared instead. They also call that Kepler's constant. That would just be gm over 4 pi squared. All right, so if you just flip everything, you can also use r cubed over period squared, as long as you're using that same ratio in the same order in order to find your unknown for the other satellites. It's totally fine.